welcome to the Automation Loop, the reaction series. So Tim and I were talking about some AI topics a few weeks ago on one of our other episodes, and we had some more questions, and Tim managed to find some more details here. So Tim, what was it that you were thinking about?
Yeah, in one of our earlier videos, it described how the context for all the prior context gets passed up to an embedding vector. And so if I'm the next word that's going to be predicted, I just ask the prior embedding vector for all the context. There are some mechanics around that. And I think I found a good video that helps explain that. I haven't watched it yet, but I think I found a good video that helps explain that by the same author that we've been watching up to this point. I'm really excited to get into this today.
Yeah, definitely. Let's get into it. And if you're new to the channel, by the way, please feel free to engage with us, like and subscribe, and leave us comments. We'd love to hear what you're thinking as we go throughout this episode.
I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing. So don't worry if it takes some time for things to in. I think that before we dive into the computation of matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want attention to enable. Consider the phrases American shrew mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these based on the context. But after the first step of a transformer, the one
did not know that middle one, but okay.
With a vector, the vector that's associated with mole would be the same in all three of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic.
Okay, so I'm going to stop it right there. So attention is the process by which the embeddings exchange context, sounds like, to get to a better meaning of whatever word we're on.
Defining a finer nuance of the definition. Yep. Well, that was circular, what I just said. Wow. Defining a...
Tim goes to the moles. Yeah, I'm just kidding. All right, let's keep this going here.
Embedding to move it to one of these more specific directions as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non-specific direction in the space associated with lots of other large, tall nouns. If this word was immediately preceded by Eiffel, you could imagine wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, maybe correlated with
visualization, by the way. It helps explain the concept.
Things made of steel.
Yeah, this guy's good.
If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things. More generally...
So that also goes to those different vectors, like we saw in a prior video. There's a vector for Italianness and Frenchness and size and
right.
So this is
there's like a crazy amount of vectors available here, right? So like so I don't remember exactly the number, but I remember there's a very large number of vectors available.
Yeah, it depends on the size of the LLM, but yeah, there are. So this is drawing on those different vectors to point it in a more specific direction on one of the thousands and millions of axes available.
And just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how after all of the vectors flow through...
I actually think this video is starting to answer some of my biggest questions about this. I think this is tying it all together.
The network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model's going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word was, will have to have been updated by all of the attention blocks to represent much, much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word.
Okay. I'm going to
wow.
pause here.
Okay.
What I'm getting, I think, is if I'm the next word and I'm being predicted by a bunch of vectors, I'm going to ask the prior vector for its context. And that vector, that embedding, is going to have all the context from all the prior vectors. So every vector passes its context to the one that's after it. So by the time you get to the last vector, it's got the entire context of every other vector preceding it. And that helps you predict the very last word.
So this is really interesting because now it helps me understand something I've just learned through practice and I've learned how to deal with, but I didn't really understand why, which is if you're having like a vibe coding session or something where you're going back and forth with the AI over a period of time, occasionally what will happen is you go down a certain path and something is incorrect and you provide a correction. And then all of a sudden, somewhere later on in the future, it will revert back to that incorrect information. And you're like, wait, but I already told you that was wrong. And I think this is why, right? Because that whole story is getting assimilated into that as you move forward. So it essentially what I have discovered in practice is I just have to say, when that sort of thing happens, I just do a new conversation. I start all over, like, let's clear the slate. Let's be clean. Let's not have that in my history anymore, essentially. Now we understand why that's actually happening. Yeah.
Fascinating. Yeah. Yeah. This does help explain a lot of the give context to the odd behavior I've seen in the LLMs I've dealt with. Well, who was the murderer? Let's find out.
To step through the computations, though, let's take a much simpler example. Imagine that the input includes the phrase, "A fluffy blue creature roamed the verdant forest." And for the moment, suppose that the only type of update that we care about is having the adjectives adjust the meanings of their corresponding nouns. What I'm about to describe is what we would call a single head of attention, and later we will see how the attention block consists of many different heads run in parallel.
Of course.
Again, the initial embedding for each word is some high-dimensional vector that only encodes the meaning of that particular word with no context. Actually, that's not quite true. They also encode the position of the word. There's a lot more to say about the specific way that positions are encoded, but right now, all you need to know is that the entries of this vector are enough to tell you both what the word is and where it exists in the context. Let's go ahead and denote these embeddings with the letter E. The goal is to have a series of computations produce a new refined set of embeddings where, for example, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. And playing the deep learning game, we want most of the computations involved to look like matrix vector products, where the matrices are full of tunable weights, things that the model will learn based on data. To be clear, I'm making up this example of adjectives updating nouns just to illustrate the type of behavior that you could imagine an attention head doing. As with so much deep learning, the true behavior is much harder to parse because it's based on tweaking and tuning a huge number of parameters to minimize some cost function. It's just that as we step through all of the different matrices filled with parameters that are involved in this process, I think it's really helpful to have an imagined example of something that it could be doing to help keep it all more concrete. For the first step of this process, you might imagine each noun, like creature, asking the question, "Hey, are there any adjectives sitting in front of me?" And for the words fluffy and blue to each be able to answer, "Yeah, I'm an adjective and I'm in that position." That question is somehow encoded as yet another vector, another list of numbers, which we call the query for this word. This query vector, though, has a much smaller dimension than the embedding vector, say 128.
Wait, so did I hear that right? There's embedding vectors, then there's query vectors that are much smaller.
This makes me think, like, you hear so much chatter about the GPUs required to power AI, but what about the RAM? This feels like there must be just massive amounts of RAM in these server farms to store all, like, if you think of the millions of people using AI at any given point in time, using an LLM, right? Like, there's so much data that has to be stored. Like, maybe it's not that much, actually. I don't know. But it sure feels like, wow, there must be a tremendous amount of RAM, not just GPUs.
It's shocking. Yeah. All right.
Computing this query looks like taking a certain matrix, which I'll label WQ, and multiplying it by the embedding. Compressing things a bit, let's write that query vector as Q. And then anytime you see me put a matrix next to an arrow like this one, it's meant to represent that multiplying this matrix by the vector at the arrow's start gives you the vector at the arrow's end. In this case, you multiply this matrix by all of the embeddings in the context, producing one query vector for each token. The entries of this matrix are parameters of the model, which means the true behavior is learned from data, and in practice, what this matrix does in a particular attention head is challenging to parse. But for our sake, imagining an example that we might hope that it would learn, we'll suppose that this query matrix maps the embeddings of nouns to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it simultaneously tries to accomplish some other goal with those. Right now, we're laser focused on the nouns. At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces...
Okay, now we're at the key matrix. All right. So there's embeddings, there's queries, now there's keys. Okay. I got a couple more minutes left in my brain, then it's going to explode. Let's...
This is getting very sciencey in this part.
It is.
This is a second sequence of vectors that we call the keys. Conceptually, you want to think of the keys as potentially answering the queries. This key matrix is also full of tunable parameters, and just like the query matrix, it maps the embedding vectors to that same smaller dimensional space. You think of the keys as matching the queries whenever they closely align with each other. In our example, you would imagine that the key matrix maps the adjectives, like fluffy and blue, to vectors that are closely aligned with the query produced by the word creature. To measure how well each key matches each query, you compute a dot product between each possible key-query pair. I like to visualize a grid full of a bunch of dots, where the bigger dots correspond to the larger dot products, the places where the keys and queries align. For our adjective-noun example, that would look a little more like this, where if the keys produced by fluffy and blue really do align closely with the query produced by creature.
Okay, my eyes are starting to glaze over at this point. I think my main takeaways from this session are the context is exchanged between the embedding vectors by the query vector and this key vector. I'm still not sure I'm totally caught up on.
Yeah, this
query
part,
vector
the
is
end
my
here
big takeaway.
was less informational. Well, it was more informational for me and less understanding.
Yeah. Oof. Well, Tim, that got involved. We ended up just having to stop because our brains hit our capacity for thinking that day. We ran out of tokens.
Completely maxed out for the day, maybe for the week.
Yeah, that query vector, that was the gem I took away from this. That is how the context gets carried forward so that the next embedding just has to ask the prior embedding, what its context is to get all the context from everything prior. Fascinating to me. Answered a lot of questions.
Yeah. And really helped me to understand, some of the behavior that I've seen using, AI. And now I'm like, I have a better understanding of why it's happening, and helps me better use AI, I think. So obviously that's a lot of our goal here, is just to understand the underpinnings of it so that we can more better able to use it. So interesting as we go down this journey and learn more about AI. Hope you're enjoying going down the journey with us. And we look forward to seeing you on the next session. Don't forget to like and subscribe.